All right, so I'm Rocco Sedona from the Jülich Supercomputing Center in Germany. So I've got a somewhat different experience or background respect to many of you. I'm an application guy, almost purely, let's say, from deep learning and remote sensing for Earth observation. So it took some time for me to speak the same language of many of you here. But that's also good because you learn new things, and that's also the contribution that we bring to this project. And I think it's very important. So the fact that we have real use cases in this project again. So originally the plan was to focus, well, not to focus, but to talk about the main of these applications that we have. Instead, I'll mostly talk about the deep learning one, which is the one developed at JSC, and also at PCNC, that are based on a very similar framework. So as I was saying, there are many applications involved, 6 actually, different use cases in this project, spanning from life sciences to remote sensing again, then NEC 5000, which is a computational fluid dynamic library, environmental applications, which you'll hear about later in the next presentation. So a whole set of different scenarios with different characteristics in terms of computation, I/O. But so let's start talking about the remote sensing application, so that that I developed with some other colleagues at JSC. So this application is basically using remotely sensed data acquired by satellites. And it's what we try to do is to utilize deep learning models to extract information from this imagery, from this satellite imagery. But why is this relevant nowadays? So the fact is that there has been a clear trend in the availability of data throughout time in the last decade. Here I reported just a figure of the European project Copernicus, that is a monitoring program of the European Commission. And you can clearly see that the amount of data downloaded by users has been increasing. And again, this is only one source, and there are many more missions, many more programs, and a lot of satellites which are also not European. So we are talking about petabytes of data made available every year, which makes it very interesting for large scale processing. In the meanwhile, there is also, in the meantime, there is also been this other trend, which you can observe. So not only the data sets have become larger, but also models have become much larger. So for some reason, I see it a bit blurry on the figure, but yeah, I hope you can see the number of parameters. But anyway, if you're acquainted with what ChatGPT is, for example, you may know the huge size that those models nowadays have. So again, the availability of newer and bigger data sets and of bigger models actually justify the use of a large amount of resources. But clearly these tasks, these trainings are very extensive, can take a lot of time. So that is why we need to use a lot of resources, and HPC systems can help us. Specifically, one of the applications that in remote sensing for Earth observation is of interest to the community is the so-called creation of land cover maps. So land cover maps are basically these colorful maps that describe the content, well, the characteristics of the surface of our planet. So there are some very interesting products. Here, for example, there's a picture of a dynamic world where we can see a few classes, like really where you can see what what information is extracted from the satellite images. For example, the presence of a river, of urban areas, of forests, and so on, which you can imagine can be of help to track many different phenomena that occur on our planet. like the urbanization throughout time, or in case of natural disasters that may affect some areas, and have in a timely manner some monitoring can definitely help also civil protection and authorities to take decisions. So with that in mind, the application I'm talking about and we are using in this project is actually using a large data set. It's around a bit more than 500,000 images that are not simple RGB images like in many computer vision tasks, but instead are multispectral, meaning that they have multiple bands. So they're somewhat more complex, and also they are multi-class in the sense that you might have multiple classes, different patterns inside the same image, clearly. And what we did was using a CNN, a convolutional neural network, to classify these patches. But what is of interest here in this talk is that we scaled the training to speed it up, since it was taking a lot of time, and we did it using Horovod, which is basically a framework for data parallelism. So data parallelism in the context of deep learning is a sort of is a way to approach parallelization of the training. There are others, so there are other families of approaches like model parallelism, but we decided to opt for data parallelism, which was and is still the preferred approach, somewhat simpler to adopt. So what it does is basically that the data set is the whole data set is split into multiple chunks, and each of these subsets or chunks are fed into a copy of the model that is hosted on different devices, so on different GPUs of our HPC systems. So again, as I was saying, we decided to use Horovod. It's true nowadays also PyTorch and TensorFlow natively support data parallelism, for example, but still Horovod presents some interesting features, among which the fact that it offers this additional functionality library called through a library called Elastic Horovod, which in principle allows dynamic training depending on the available resources that we might or might not have at some point in time. And to do that, while the standard Horovod library relies on MPI and CCL, Nickel, what you prefer to call it, the NVIDIA communication library, actually Elastic Horovod works with Glue. Again, so malleability here, a few talks ago, last hour, Thailand gave a much better and more precise definition of what it is, probably, but still, it's what it means for us is to be able to dynamically change, resize our application at runtime. So is it relevant for us with guys with deep learning application? Well, yes, it's very interesting for us. Why that? So deep learning applications, deep learning models, again, they can have millions up to billions of parameters. They are typically compute-intensive tasks. And depending on the problem that you're solving, it can be also I/O intensive. So it depends, for example, thinking about a generative model where you also not only read a lot of files, but you might also create many, then in that case also it can pose some challenges in that regard of I/O. So finding a sort of balance is definitely of interest for our applications, also for deep learning. But again, there are multiple challenges. Some are scientific challenges, some are technical challenges that we faced. So scientific challenge, the first one that pops in my mind is a known problem. That is the problem of the batch size, because it poses a problem when you scale up to many devices and your actual global batch size grows, then it can hinder your training. So this is something to consider when taking choices and decisions. But also another question is when and if is it safe to increase or release resources at runtime? And that said, let's say that we know when. How can we do it technically? So how can we shrink and expand the allocated resources during training? Well, these are all important questions that we need to tackle. Let's say that again on the question of the batch size, there's also this consideration that one needs to take. So the smaller the batch size, clearly the longer the training will take. The larger, the shorter, in principle, you might think. Yes, up to some point. And also, we need to consider that there is this sort of trade-off. So there's a sort of Pareto front that we need to optimize and find a sort of optimum to see what is the optimal point between the batch size and the available resources that we have. The problem of this is that, again, we have a sort of upper bound in the sense that it's known that for batch sizes above 8,000 samples, it takes actually, so the scaling is not so linear anymore in the sense that you actually give this sort of wall which you cannot cross easily unless you adopt more advanced optimizers. But again, it also depends on the specific scientific problem you're trying to solve. So we have this upper bound on the batch size, and lower bound is again smaller batch size means very long trainings. But then the problem is also that it depends also this batch size, and the optimal batch size depends also on the phase, on the stage actually of the training in which we are. So, for example, it has been empirically observed that at the beginning of training, it's better to have smaller batch sizes. And actually, that might be interesting also in terms of deciding how many resources we should allocate, because it means that we can use less resources, less nodes, smaller number of nodes at the beginning. And then after a few epochs, we can somewhat increase the batch size, and we can do that allocating new nodes, for example. Let's say that at some point after, I don't know, 100 epochs, we reach an accuracy that is acceptable. Then we might also do something, again, shrinking the problem, release some nodes. Why? Because maybe we want to allocate those nodes to other jobs that have a higher priority. And instead we can, since we already have a good model, we can wait for an even improved one for a bit longer. It's just a use case, but I mean, it's to explain you that it makes sense to use this to adopt malleability also in these kind of problems, and that we can, with these limitations in mind, adapt to a dynamic resource allocation. Again, how to do it technically? We had first some trouble. Well, not really with shrinking. Releasing resources with Slurm was relatively straightforward. Then we tried to increase the size of the allocated resources in a single job, but we failed, and it appears that it's a problem of the latest Slurm versions. But luckily, there are some technical solutions to that. So the first one, which was, let's say, our plan B, to be honest, was considering checkpointing, so sort of a start and stop approach, where our application at some point after some epochs would save the checkpoint, and then when we need to change the job size, we just stop and again restart with a different number of resources, of allocated resources. This can be done. It's relatively simple. It's already implemented, and it's something checkpointing is implemented in all deep learning frameworks. But it means also longer time to convergence in the sense that you probably waste some time waiting for retrieving older checkpoints and restarting the job. So our preferred solution is again this second one, which is instead allocating multiple jobs and use some sort of controller to dynamically allocate, release resources and update the host file with the available resources. And the good thing is that if we are able to do so, to update this host file, Elastic can automatically adapt to the newly made available resources. Here, I think we are finally at a very good point in the sense that really just this morning we had some very good advancement in that regard. So I think we are definitely opting for these solution that was anyway our preferred one. But yeah, so as I was saying, there are these kind of applications pose several challenges. So both scientifically, technically, and dealing with this complex setup is it's clearly challenging. But I think that it's also good for the project in the sense that in this project in Admire, again, we have, as I said at the beginning, we have real applications, real use cases. So not only by examples. So we face, let's say, the reality of researchers and their problems, which I think is an added value of all this work. So also preparing for, let's say, the end of the project, the fact that we are able to deliver something that is useful also to others, to the broader community, I believe there is of great interest. Also for us application guys, let's say, who are users of HPC, but need tools to adapt to this continually changing world where we need more resources, more computation, more I/O, and we need to understand how to find this trade-off. Again, there's a lot to do still with these applications. We're entering the era of exascale, which will bring us again many more challenges, but also a lot of opportunities. So again, if you have any doubt, questions, or want to know more, you know my contact here. I thank you for holding still till this time, which might not be easy. And yeah, again, if you have any question, please, yeah, tell me. And I salute you with Francis Ford Coppola. And
but it's not the end yet.
yeah, I know. It's the end of my presentation.
Yeah, as you can imagine, there are no questions at this time.
Too late.
Okay, I have one question.
Yeah.
Yeah.
So I understand that you were able to unlock today the problem we had for the elasticity, okay?
Yeah, exactly, Javier. And I had a talk with Thailand and Javier, and also Wojciech. And actually, yeah, Javier told me that he explained me that the solution that he used to solve this problem of SSH that we were having. So basically, our application was timing out. Because it wasn't able we weren't able to access resources allocated through another job. Basically.
But this is in your place or
This is in Torino.
in Torino?
Yes, but we were not able, and basically modifying the configuration file, we were finally able to do that, and we tested it this morning with Wojciech.
And you're going to test in your place?
Yeah, sure.
Because we need to know if it's, I mean, if this is the usual configuration or.
Yeah, so I know that for sure that in the big machines in HSE, they don't allow it. So we need to find probably a workaround for that. In the prototype machine that we're currently using, probably it will work, but we need to test it out.
Okay.
To extend it to other big production machines, we need to understand what is the, let's say if there is some way to request sort of policy, I don't know if policy change or policy adaptation or something,
Okay,
but we're definitely going to test it out.
okay, good news. Thank you.